Buenos dias, good morning. I think everybody may need their headphones. I just want to start by saying it's really a great honor and pleasure to be here today with all of you. And I want to thank my new friend Magdalena and all of her amazing team for putting this important meeting together and for letting me come here and share our research and be part of this. So I want to really convey my gratitude to all of you. I am going to be one of two speakers today who will be presenting. Can everyone hear? The translation is okay? See? Okay. I'm one of two speakers who is presenting research from an area that is broadly known as cognitive neuroscience, which is the link between cognitive psychology and neurobiology, neuroscience. Myself and Dr. Manolo Carreras, who is not only doing the same work, but we actually collaborate. So you'll see some overlap in one study that we did together, looking at how the brain develops reading circuits, and by circuit we mean connections and systems, in different languages, including English, Spanish, Hebrew, and Chinese. And so you'll see a little bit of how we've learned about maybe what's universal in reading, irrespective of the specific writing system, in terms of how the brain masters the challenge of learning to read. So you'll be getting a lot of information on different brain regions, names of different areas of the brain. Most of you are not studying neuroscience, and there will be no quiz in the morning on whether you can remember the difference between the angular gyrus here and the supramarginal gyrus and the superior temporal gyrus and Broca's area. This is not the purpose of this talk today. I will refer to all of those things, and I'll show you lots of pretty pictures of the brain, because that's what the data looks like. But my job, if I do it right, is to give you an understanding of the bigger picture, which is what is the promise of neuroscience in education and in helping children who struggle with various kinds of language and learning difficulties? What's the promise of studying the brain to education? And it's important because we're at a time where neuroscience is progressing incredibly fast in many areas, from genetics to neuroscience to cognitive science. There are really major advances happening in our understanding of the biology of learning, language, and memory. And so it's natural to think that all of this great progress is going to translate into the classroom. And it's also right, I think, to say that it should, pero. It is also important to recognize that we are in some ways, still very early in our understanding of the brain and all of its complexities. And it's very important that educators, people who work with children, are able to understand what we know and, importantly, what we don't know. What are the limits? Because there is a tendency, and you probably see this at different meetings, for people to come in and say, this is a neuroscience-based curriculum. It's based on the brain, so you have to do it because it's the brain. And then people like me show you pretty pictures of the brain, and they say, well, it must be good science because it's got a picture of the brain, right? And sometimes people are perpetrating overstatement and actually not very seriously understanding what it means to educate, what it means to create curriculum. So many of the speakers here today, all of whom I know, will be speaking about how to instruct literacy, how to diagnose learning disabilities, how to remediate those disabilities. As a neuroscientist, cognitive neuroscientist, we work together. We know about measuring the brain, and my colleagues in my laboratory and around the world who understand education and pedagogy and best practice are working in conjunction. So what am I saying here? I'm going to be giving you a lot of stuff, and you're not going to remember every detail of all the subtleties of the brain. But I'm going to be addressing this bigger issue of what is the promise of neuroscience in understanding development and in education? What are the limitations of what we currently know and don't know? And in many ways, what do we actually know that is relevant to education right now? And I'll try to do all of that. And I'll be talking about, I keep referring to 3 broad questions. And this is another way for people who are not in neuroscience to follow this talk. Uno, how does the typically developing child build circuits or connections or pathways that support fluent and efficient and adequate reading and writing? Uno. How does the brain solve the puzzle of building a reading circuit when, in fact, reading is really not something that we have evolved to do? And I'll get to that in a minute. So that's question 1. Question 2 is, how do children who struggle with reading, whether due to brain-based challenges, developmental dyslexia, or due to early environment, poverty, lack of access, how do these children develop circuits that are different than those who are succeeding? So question 1, how does the brain build circuits when all goes well? And question 2, how does this differ when it doesn't? And question 3, the muy importante question, especially for educators and parents, is how does optimal instruction, treatment — I thanked you when I started, and I'm honored to be here. So how does treatment, remediation, optimal instruction, good curriculum, good pedagogy, how does that modify those brain differences? So I'll keep coming back to this. The first part of my talk, how do typically developing readers go from being listeners and talkers to readers and writers? And that's a challenge for the brain, for sure. And I'll share what we know, what we don't know, and where we're going. Then the second question again, how does all of this differ in reading disability? What is reading disability? How does it present? How is it measured? What are the brain signatures? And 3, the most important question, how can we design learning environments that make those differences minimal, that change the brain in important ways? So again, when you finish with my talk and with Manolo's talk, you're going to see a lot of sort of recent cutting-edge work in many fields. But it's important that teachers and educators know this field, are aware and studying what's happening, and are skeptical about claims that are often made on neuroeducation by people that shouldn't be making them. Sometimes people that cite our work inappropriately. We're the ones who are sort of sitting in the weeds, and we are here to tell you, I believe Manolo would agree, that we can't just simply claim that all questions of education are answered because we can map the brain. But I tell you with my soul that I believe over the next 10 to 15 years, we're going to see tremendous delivery from this emerging understanding of how biologic systems learn, on how we shaped an optimal learning environment, both for typically and atypically developing children. So, reading. This man sitting here took this picture. You remember Manolo in Taiwan? This is a god in China, in Taiwan. And he was an ancient wise man. And he's revered in China and in Taiwan. But I love this picture, and I asked Manolo to take it because it shows you what good reading is like. Here's a man who is able to go beyond the immediacy of talking and listening and gather information about history, language, culture, art, simply because he's learned to crack a code, to connect written form to natural language systems. But in order to do that, he needed to have good focus and executive function. How many of you have heard the term executive function? Most of you, okay. Not all. He has to have very good selective attention. He has to have good language skills, good phonologic awareness, good basic principles. And with all that in mind, he can explore the universe. So reading is a really complicated thing, but once you've got it, it's a source of great information and expansion of knowledge. So I love that picture. Not too important for the talk, I just like the picture. So I begin with the obvious that people in this audience understand better than most. One, the acquisition of fluent reading is super important in the modern world. And significant numbers of children in all languages, whether they are transparent languages, easier to decode like Spanish, or less transparent languages like mine, English. Significant numbers of kids in all languages will fail to acquire age-appropriate literacy skills. And we already saw in the initial presentation what some of the numbers can be on that. For many, this can be attributed, especially in under-resourced areas, to a lack of adequate opportunity to learn. And unfortunately, and this is really true, if reading is not taught well in an evidence-based way, which is what we're all going to be talking to you about today, you can kind of mess up the ability of the child to become an efficient reader. So we call this curriculum casualties. And that one of the reasons meetings like this are so important is because we can share what's known from research on best practices for teaching reading. But for many kids, learning to read is delayed, is inhibited, is made difficult by environment. But for significant numbers of kids, even in over-resourced, well-resourced environments, reading is inordinately difficult. These children are not slow. There is no meaningful statistical relation between intelligence and reading disability. Reading disability is a brain-based difficulty in operating on language structures and in mapping and connecting visual systems and language systems. They are not related to intelligence. Many children with specific reading disability, or what is often referred to as dyslexia, are extremely bright. But because there's no relation, there's bright, there's kids who are average, there are kids who are below average. It is not a sign of how smart or how lazy or how hardworking you are. It is a real and difficult challenge that's rooted in how the biology of learning struggles for some content, in this case reading and language, relative to others. And then there's the even worse case, which some of you working in who are working with schools that might not have all the resources they need. You're going to have combinations of kids who have some of these brain-based differences that can make reading difficult while other things are just fine. And they have lack of access to early vocabulary and experience. We would call this in English a double whammy, a combination of factors, internal and external, that make reading especially difficult and difficult to remediate. So, reading is important, and significant numbers of kids in all countries struggle for a variety of reasons, some congenital, internal, some environmental. I want to take a few minutes because, again, you as educators are dealing with often families that might not know a lot about early brain development and about what babies and prenatal environments need to be. Because in many ways, and this is true, good reading, which should begin when the kid is 6 or so, needn't begin too early, begins from birth when it comes to oral language development, richness, vocabulary, stimulation, and even starts from prenatal conditions, preparing the brain to be healthy and able to code, learn, attend, and remember. So it's obvious, but it's often forgotten, that success in school starts with good beginnings from the prenatal stage. And so because that's so important, I want to share with you just a couple of things that come from connections of early risk and later reading, things that are kind of important markers that arise from the neuroscience of birth to 5, birth to 6 development. And some of these factors include, of course, malnutrition, exposure to drugs, alcohol, nicotine, neglect, which is a massive, if the child whose brain is built and wired to learn to talk and listen is not given adequate stimulation or attention or support, these brain systems will be compromised. There's a lot of research going on these days on exposure to violence. If babies and toddlers are exposed to extreme stress, the brain actually perfuses certain chemicals that are meant to handle stress and arousal and response, but in over-perfusion are actually damaging the brain in important ways. And so these early experiences are crucial in building success. And then, of course, stimulation. So let me just give you an example, and this is kind of an example of how looking at the brain very early can help us understand where risk really begins. This is a study that was done by another group. Most of the data I'm showing is from our group. This is a study done some years ago in children who had been exposed to, prenatally to nicotine, moms who smoked. We all know these days, mom, don't smoke, okay? But some people smoke. And what are the consequences? And what we can see is that when these infants were recorded using something called an EEG cap, which is measuring electrical activity on the scalp, brain activity, one of the ways we measure the brain, we could see, this group could see that even these newborns and infants were showing attenuated responses to speech stimulation, the main difference being whether they had been exposed or not exposed to nicotine. Now, this is a strong claim and a finding that needs to be replicated in other contexts, but there's plenty of data suggesting that this prenatal exposure to alcohol, fetal alcohol syndrome, to nicotine can have a damaging effect. And we actually were part of a project at Yale, in my lab, working with psychiatry, where we took children who were adolescents and who had been either exposed to nicotine in utero or not. And we studied their brains very carefully at age 13. That's a long way from birth. And what we found when we mapped the activity systems that are associated with attention and response control, selective attention and executive function, and memory and language, that we found subtle anomalies, difficulties. These children were, functioning normally. They're doing, for the most part, okay. But even in adolescence, we could see the trace of this exposure that was creating what you might think of as a less than optimal organization for memory, language, and attention. And there's plenty of data. This just happens to be ours. There's plenty of data from many labs in many countries showing that these early factors, nutrition, exposure to alcohol, nicotine, drugs, can have long-lasting and persistent negative impacts, which will, of course, impact education. there's a lot of work on what babies need to prepare themselves to master literate language later on. And the most important thing babies need is to be talked to a lot. Talking, 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 talk. Lots of vocabulary, lots of language. I think, Florencia, you'll probably talk a little bit about the oral language and reading problems that arise. We'll get to this in a few minutes, but we are wired as a species. We're sort of born to operate on natural language, listening and speaking. We're wired to talk and listen. We're not wired to read, and we'll get to that in a few minutes. But one of the things that the brain needs, babies, in order to perceive speech and to develop rich language, don't need to go to baby school to be taught that this is a ba, and that's a ga, and that's a da, and that's different, do they? But what they need to do is to let the biologic specialization along left perisylvian regions, I'm starting to use terms, that are involved in expressive and receptive language, for those systems to be tuned on a principle that is referred to as statistical learning, which just means that the brain picks up information, enriches its vocabulary due to early exposure. And that enriched vocabulary and that enriched language experience facilitates very rapid rise in early language competence, oral and receptive, expressive and receptive. If the child is not given adequate exposure to rich vocabulary due to, in many cases, environment and poverty and lack of access, lack of books, lack of exposure, lack of knowledge on the part of families sometimes, there are consequences that present through life. This is a very famous study done in the United States by Hart and Risley, in which they looked at children who were growing up in extreme poverty, in average socioeconomic status, or in privileged. And what you could see is already by 24 months of age, the average number of words that the child had been exposed to and could process was already beginning to diverge for the children from the upper socioeconomic status, from the enriched environments. And here's the sad thing, folks. If you track these kinds of things out in time, the rich get richer and the poor get poorer. And what we see in school, and I've been involved in a number of longitudinal studies at Yale that looked at children with early language issues and reading as they enter 4th grade, 6th grade, 10th grade, and high school. So these early exposures to rich language, preschool language exposure, if they aren't there, that diverging curve will continue to diverge into school. It's called the Matthew effect. Matthew, the rich get richer and the poor get poorer. Here I am in the country of the Pope. I had to use that. The rich get richer and the poor get poorer. And so this is very important that we understand that reading in 1st grade, which involves these visual squiggles, letters, and syllables, is somehow linked to these early exposures, to these early factors. So now, on to the question number 1. How does the brain develop circuits that allow you to be a fluent reader? Well, first of all, what is a fluent reader in the early stages in elementary school? I will say it like this. A skilled, fluent reader is able to decode the word bloody fast. In fact, I don't know, we can discuss this. If you use EEG and some other measures or inference from eye movement, you would say somewhere on the order of about 250 to 300 milliseconds after the stimulus is seen by the retina, you begin to access the meaning of the word. If you are a skilled reader, you are really fast. And if you're not if you're really fast and you're reading a sentence, and each word can be pulled and plucked quickly, then you can put your attention onto the grammar, onto the meaning of the sentence, and beyond. So skilled readers in any language are bloody fast at recognizing words. That's one. Somehow the brain does something that builds a circuit that allows you to go from eye to meaning in the blink of an eye. Second thing, if you give that good reader a word that they've seen a zillion times, and these are called sight words sometimes in education, they're going to be really bloody fast. If you give a skilled reader in any language, alphabetic language, a nonsense word, this is a word they've never seen. It could be a word, but it just doesn't happen to be yet. It will, of course, take a little longer, but if you do your experiment right and you measure carefully, it can be something like 50 milliseconds. 1,000 milliseconds is 1 second. So if you're a skilled reader, you can read nonsense words, things you've never seen, that need to be decoded, almost as fast. You've built a system that can process novel and familiar words ridiculously, ludicrously fast. And the premium is on fluency and automaticity and accuracy. And as we get to the second question in my talk, what is dyslexia? What is reading disability? What's the brain basis? The first thing that you will know, and that will be discussed by many speakers today, is that these bright, beautiful kids who do a lot of things really well don't decode words bloody fast at all. Word reading is slow, labored, and error-prone. And we need to understand why the brain is doing this. And then, of course, ask that third question, how do we change all that with treatment and remediation? Those are the three topics. So let me begin by just rephrasing something I've actually already been alluding to, which is we're wired to talk and listen, and we're not, I claim, I insist, as they say in Spanish, I insist, we're not wired to read and write. Now, written language is a relatively recent invention. It's only been around for 5,000 years. As a species, we have a great deal of biologic specialization for perception and action in speech. We need to be stimulated and given rich experience for those statistical learning systems to tune up and allow the child to start gabbing like me and listening like I should be doing sometimes. That's what we are wired for. There's a great deal of brain machinery. But as Stan DeHaan likes to say, who's an important thinker in brain and reading, reading is an exercise in neuroplasticity or neuronal recycling. And what that means is taking systems in the brain, like systems that do language, receptive and expressive in left perisylvian cortex, where I'm pointing, visual areas that code the letters and the complex arrays, associative learning areas in the parietal cortex and other regions, cortical and subcortical. You'll see this as we go through it, and you won't be quizzed tomorrow on the name of everything. But each of these areas needs to transform and take on a new job in order to be a good reader. What is that new job? Find a way to go from the areas that process the visual form in the occipital lobe into the language system so that you can operate and understand and comprehend and think. Bloody fast. How does the brain find connections or pathways that make reading easy? And is that different in Spanish, Hebrew, English, Chinese, Hindi, Finnish? We study all those languages. And my claim is that it's going to be very similar. So, this is a schematic diagram that I think will help you as I enter into the brain. This is not a brain diagram, this is a cognitive diagram. But it gives a little sense of what it means to be having a good word reading knowledge. good word reading knowledge, or what Chuck Perfetti calls high lexical quality, involves strong bidirectional associations and connections between the three features that make up a written word: meaning, or semantics, phonology, or the spoken form, the consonants, the vowels, the syllables, etc., and this weird thing that we invented 5,000 years ago to represent the forms of phonology, the alphabet, or in the case of some languages, Hindi and Korean, syllabic, or in the case of Chinese, an entirely different writing system. Your language and my language both use the same alphabet, so they're alphabetic. But when you are 6 years old, 5 years old, and you're coming into school, as Florenzia will no doubt tell you, you better know many thousands of words because of that early vocabulary I talked about, in terms of their spoken form. So the connections between meaning and phonology need to be robust, and frankly, you need a lot of them. Because the richer the vocabulary, the more you're strengthening this. But if I show you a bunch of squiggly things we're going to call letters, there are no connections. So somehow, in order to go from I to meaning, bloody fast, 250 milliseconds or so, whatever, you need to build connections. And the most important connection for the emergent reader, and you'll hear this from a lot of speakers, is mastering the principles of grapheme-phoneme learning. This base of the triangle is actually the base of reading. And it needs to be instantiated in such a way that you can build all sorts of connection to the richness of word meaning. And when you're reading that sentence on the page, each word is effortless, automatic, fluent, and accurate, and you can pay your attention to the meaning of the author's wonderful story. If you struggle with this building of this schematic, where does that schematic live? Not in your elbow, not in your rear end, but of course in the brain. And this is why we need to study the brain to understand how the brain solves this puzzle when we have not really evolved so much to read and write. It's a relatively new skill. It's a cognitive challenge to somehow reorganize the brain or do this neural plasticity in order to read well. So, the brain. Ta-da! Okay. You ready for the quest? No test. Sorry. So in the left hemisphere, we have the frontal lobe, we have the parietal lobe, we have the temporal lobe, and in the back of the head, we have the occipital lobe. So this is a sagittal left hemisphere view. And this is a very simple, somewhat overly simplified way of talking about oral language I will give you as your first exposure. The brain is complex, and there's lots of systems involved in oral language that are not in this schematic. But for the most part, here's what we know. For most neurologically normal people who develop good spoken language skills, there is a great deal of brain specialization along this left perisylvian region, and that there is tissue or populations of neurons in and around the inferior frontal gyrus, which we know from lesion studies. These are studies where you study what happens when an area is injured, that are important in expressive language. If this region is damaged, you will often get an expressive language deficit and often an agrammatic deficit as well. But sometimes receptive language is more or less spared. So this is sort of the action, the productive side. But it has to work in conjunction with other regions. This is called Wernicke's area, and again, this is an oversimplified initial sort of schema for you. But the Wernicke's area, if damaged, is often associated with receptive language problems, but not always with expressive ones. So we know that to an approximation, there is some division of labor along this left hemisphere for receptive and expressive. Now, in normal conversations, these two systems need to work in an intimate feed-forward and feedback way. And there are connections in the white matter tracts that connect different parts of the brain. There's a region called the Arcuate Fasciculus. Don't need to write it down unless you want to. And the Arcuate Fasciculus is a set of fibers that essentially connect the receptive and expressive language areas. So there is an important role of other areas in receptive language, including some role for certain right hemisphere structures. But for now, I would say if you were to take an adult and you were to damage by stroke or injury or accident the left hemisphere, you are much more likely to lose language than if you damage the right hemisphere. So even though it's not, and this is not all the silliness you may read about left brain people and right brain people, that's all neuromyth nonsense. We're talking about biologic specialization. The left hemisphere is important, so is the right, but the left plays a crucial role in talking and listening and all that stuff that we're doing even if we don't know how to read. But the area of the brain that sees is the occipital lobe in the back of the brain, right? And the occipital lobe is processing the letters, is processing the visual information. And so what now has to happen is, in order to build this complex orthography, phonology, semantic diagram that I just showed you, the brain needs to find solutions for mapping from the visual representation and taking advantage of the machinery for talking and listening in the process of reading and writing. And I'll say this once, and I'm going to say this about 10 times. So this is your first exposure to something that was rather annoying, and it's this. Good reading, fluent reading, is, as one of our famous linguists at Haskins Laboratories once wrote, parasitic on speech. Now, parasitic sounds like a bad word, but it doesn't necessarily mean bad. What it means is that for a skilled reader, the success in reading involves being able to use the same machinery that support receptive and expressive language in its natural form, oral, and be able to co-opt and use them and integrate them efficiently as part of the reading circuit. And I'm going to show you over the next part of my talk a lot of data that suggests that children who succeed in reading and those who don't differ in the ability of these language areas to be utilized, co-opted by reading. And if I'm right and all these data are right and I prove my point to you, then you better, damn it, be thinking about links between oral language and reading early on. Instruction should pay attention to language early on, if all of these arguments. This is where the neuroscience I'm going to show you in some ways will conclude by proving what your grandmother might know if your grandmother were an expert at reading. Reading depends on phonology and language and these connections. So let me show you what I mean. This is what needs to happen in order to get from I to meaning fast. We live in a time, and you'll see this in my talk and in Manolo's, where we can actually measure living, acting, normal brains while we do brain imaging. So we're not bringing these machines into your classroom. We're using these to understand the brain so that we can develop a better understanding of how to teach to the brain's capacity. We're not talking about bringing MRI machines into your classroom. This is the science that will lead, we hope, to, with some humility and patience, to neuroscience being able to actually positively inform the ways we think about learning. One of them is called an Fmri. This is the system I'm going to be mostly using. Most of my data is MR. Most of yours is MR, or you have some EEG today? A little bit? Both? Okay. So An MRI image is, and I'm not going to give you a physics lesson here, but I'll tell you what happens. This is a magnetic field. It's entirely safe. We do lots and lots of fMRI studies to map where critical circuits are in the brain while you're sitting in that scanner, reading, listening, thinking, whatever. We can map the areas that are active with a fairly precisely, within a millimeter or so, of where they are in the left, right hemisphere, frontal, parietal, etc. So when you're in the scanner and you're doing a task, there is technically a perfusion, a change in oxygen content of blood in the brain. When a population of neurons is working hard, there's a change in the flow of oxygenated blood in order to replenish those neurons, and by some magic of nature and physics, we can detect that change using this machine. So in a sense, if I tell Magdalena, imagine a pink chicken, and she closes her eyes and she imagines a pink chicken, the pink chicken area of the brain, wherever it is, it's not really there, will be active. And when that activity occurs, there'll be a change in the blood flow, and that can be detected fairly precisely. At the same time, we use other kinds of imaging. This one is EEG, which measures electrical activity of the scalp. For any of you who are studying these things, I'll just say this simply, and I won't go into the weeds. We often use these two kinds of imaging together because fMRI tells us where critical circuits are, and EEG can tell us the timing of activity across those circuits. And so a proper understanding of the brain, one that's deep and sufficient to maybe inform how we think about learning, involves using all of these amazing, crazy new technologies in order to map and understand how children learn to read. So that gets us to the next phase. Are you with me for now? I hope so. I can stop and we can all drink coffee if you need. But otherwise, stay with me. This is an fMRI experiment. Now you're looking at real brain data. Wow. And it is being shown on this schematic. And this is a simple experiment where the child, or in this case, a young adult, is in the scanner, and they're doing one of two things. This is not hard. You'll follow me. In condition one, they hear words, and they have to make a judgment. Is it a living thing like a cat, el gato, or is it an object like a chair? Chair? Okay. Yes, no. Stupid, dumb, simple. And I can identify the areas that are involved in perceiving spoken words, natural language. In the second condition, they do exactly the same thing, but the stimulus comes to the eye in the reading. And so, same task, same stimuli, more or less, and we are able to say which brain regions are involved in spoken recognition, which ones are involved in reading, and which ones are overlapping. So if you look at the data, this is based on statistical analyses. I'm not going to go into these, but I want you to get this one. Stay with me now to understand what I'm showing you, and the rest of the talk will follow. When we look across the analysis of these brain data at different areas in this computer space, we find some areas, in this case shown in red, that respond uniquely to the spoken word. Where are those regions in red? If you know anything about basic brain, they're in the auditory cortex. This is the primary sensory cortex. If I don't see activity there, I might as well go home and go into another business, because this is the speech recognition. And in that primary, secondary auditory cortex, the response is mostly to the spoken word, to this sound. In the same way, in the occipital lobe, in the back of the head, there are populations of neurons that are responding uniquely to the printed word, because it's visual. And that's not interesting. If that's not there, I go home, I go into another field. What's happening in many of these important language areas, including Wernicke's area, the angular gyrus, the supramarginal gyrus, the parietal, the inferior frontal gyrus, Broca's area. What's happening in this schematic is we're showing this as a green color. All we're showing you is that in a skilled reader who's not struggling with dyslexia, when these important perisylvian regions do not care any longer, they don't give a darn whether the stimulus came to the eye or the ear, because they have transformed and they now operate on words in an amodal, modality-independent manner. And why am I driving you crazy with this green and with this amodality? Because it turns out, I'm about to show you that that predicts beautifully whether a child's on the right trajectory for reading by 3rd grade or not. So again, in green are those brain regions in left hemisphere, perisylvian, and extended cortex that in normal readers are able to take spoken and written language and just not care which one it is, merge them, combine them. What does early teaching of reading involve? Combining auditory and visual. This is a physical signature in the brain. And there are major areas. Sorry, I hit the wrong button. Wow, that's not a good sign. See. So we're not going to go into the details, but those of us who study these circuits, we go into great detail on some of these areas. And one important distinction, and probably, Manolo, you might actually end up referring to this, is a distinction between dorsal, which means toward the upper part of the brain, and ventral areas. These parieto-temporal and inferior frontal areas that are shown near the top. And if you look at my fingers, here and there. These regions are very much critical in learning to initially solve the puzzle of binding orthography, phonology, morphology, and semantics. Building that triangle depends on the feed-forward, feedback dynamics of these regions and some subcortical areas like the thalamus and the basal ganglia, which I won't go into. But the child who's just learned to read and now understands that they can sound out anything and they can read it, they're not automatic in 1st grade. They're not fast. They're just accurate. And it turns out that we have evidence that as children who are typically developing, remember, this is still question 1, how does the brain build a reading circuit? It turns out that as children go from being beginning readers and all goes well, and they have good instruction, and they're not struggling, they're remediating their difficulties, there is a shift to a more reliance on this lower region that's come to be called the visual word form area. It's just a word, just a term. In the left occipitotemporal cortex, that is a population of neurons, several populations, that are particularly good at rapid pattern recognition. And in a child who is developing good phonologic knowledge and reading, this area begins to take on a new function. It takes on a function of being like an expert system that allows you to get from I to meaning bloody fast. So fluency and automaticity in most languages that have been studied to date involve these learning areas and the training of a fast mapping system that allows fluent decoding. So we're beginning to answer this question of what we know about the topology of brain systems, learning systems, expertise systems. This is the most important last fact on normal reading. We're back to our red, green, and yellow thing again. Sorry. Early reading, our research at Haskins Laboratories, and you know all the old people, Liverman, Shankweiler, and the others, showed very early on that good reading depends on phonologic awareness and on good oral language, written language connections. So one of the most important predictors, and several people will talk about it today, is this sort of meta-linguistic understanding that spoken words have smaller parts, and this is referred to as phonologic awareness. When it's at the level of the phonemes, the grapheme phonemes, it's phonemic awareness. This is a child who's about to learn to read needs to understand that spoken words are made of smaller parts, and that those smaller parts can be represented by squiggly lines, letters, or aksharas, or Chinese radicals. And it turns out that that's not so easy for many kids to really appreciate the linguistic structure of spoken words. And one of the best predictors, listen, of what reading will look like in 3rd grade is the early ability to understand that spoken words are made of parts. So it is a crucial, actual causal. There's a lot of debate, but the debate is wrong-headed. Phonological awareness is also improved by learning to read, but it also causes and drives it in preschool. So this language stuff that you're going to hear about today is called phonological awareness and other things. Phonologic working memory, rapid naming, and other things that reflect language. So for kids who are, I'm going to be talking about with dyslexia, the vast majority do not present with visual problems as a cause. The vast majority overwhelmingly present with difficulties in phonological processing. That's just simply a fact at this point of data. And that means that we need to pay attention to that. So in this experiment, we actually looked at children and put them in the scanner. It's safe, but annoying. Hundreds of kids in New Haven, so, including my own when they were little. Now they're adults. I just became a grandpa, and eventually we'll put my granddaughter in the scanner because it's safe, totally safe, but annoying. Okay, so we ran the study where we looked at a large number of children at age 6 and 7. So these were emergent readers. And we know behaviorally, and several people will talk about this, that children who are on the right trajectory for reading, are doing well, usually have better phonological awareness. So we had kids who had really good phonological awareness, really impaired phonological awareness, and average. If a child is showing phonological awareness that's really difficult, and these phonologic skills are really not coming along, that child is at extraordinarily high risk for dyslexia later on. Okay, now, one important thing, and the translator knows this because we talked about it yesterday. This is muy importante and extremely annoying. Are you ready? When you look at these are axial slices. These are images of the brain from the top to the bottom. And due to radiologic conventions, the left hemisphere, the language-dominant hemisphere, is on the right side. It's as if you're looking this way. It's just the way radiology. So this is the left hemisphere. That's the frontal lobe. That's the occipital lobe. That's the cerebellum. Left hemisphere, right hemisphere. Just keep that in mind, that I'm showing you the left, which is important for building these circuits, shows up on the right side of these scans. That's it. We just keep that in mind. In the left areas that are involved in speech and language, we found a very important relation, and it goes like this. These areas that have evolved by evolution for spoken language will respond to spoken words quite nicely whether you have good phonological awareness and are in a better position to learn to read, or you have poor phonological awareness. It doesn't matter because these systems are built for speech. On the other hand, if you have good phonological awareness, we already at age 7 can see that these regions are beginning to respond to print. So the critical thing is that if there's a deficit in phonological awareness, these areas that need to be transformed are not responding to print. So this green, this change is not happening. So the areas are responding just fine. Oh, okay. I didn't realize. I thought we started a bit late, but okay. So anyway, so these areas are responding to print, and this is a sign that the child's on the right direction. How do we know this? Because 2 years later, we followed these children, and we published this study in one of the journals in our field, in which we asked, what was it at age 7, when children were emerging readers, in the brain that predicted their reading 2 years later? What is the single most important factor in brain circuits that predicts whether you're going to be reading well in 3rd grade or poorly in 3rd grade? And so, once again, we looked at the areas that respond to print and speech. I'm going to go a little quickly on this because I need to make up time. What we found is this. This is a very sort of an important slide. Let me explain what it means. When we asked what predicts reading scores on standardized testing in 3rd grade, which is Woodcock-Johnson broad reading at age 9, from the brain at age 7, what predicted was not what the brain looks like when it's reading or listening in a vacuum, but whether it was using the same neurons to do both jobs. That thing I talked about is the single best predictor of reading outcomes. That somehow this early change of language systems to become part of the literate brain, this plasticity, this neuronal recycling, is the best predictor of whether kids are going to be struggling in 3rd grade or not. And it reinforces ridiculously and obviously that early language and reorganization and plasticity of speech areas is critical in reading outcomes. And so now we ask a question. Is this just because it's English, which has a complex writing system? Or is this universal? And what are the implications for the classroom? If this transformation of speech receptive and expressive systems to be co-opted and used by reading so that you can get from I to meaning ridiculously fast. If that's what this is all about, then we need instruction that emphasizes language, and we need to be looking at babies preschool and up to make sure language development is on the right track. Okay? And so in some ways right now, this is neuroscience confirming what good teachers know. But I'm showing you where we are so you can see where we're going. But first I want to ask the question, not just what does this imply about practice. We all know what it implies about practice, and many speakers will talk about it. But also, what is it? You know, many people say, well, Spanish is a phonetic writing system. If you know how it looks, you know how it sounds. English, how many of you read English? Most of you, has words like P-I-N-T, which should be, by rule, pint, but is pronounced pint. So English is not so transparent. It's muy loco. No, it's not. English preserves morphology at the expense of phonology. It's a different way to build a writing system. But it does take longer. The caustate studies in Europe show kids take longer to master English because of the one-to-many mapping between graphemes and phonemes at the base of the triangle. It's a bit harder. But kids end up in the same place, and there are advantages to any writing system as well as disadvantages. But Spanish is very phonetic. It's easier to read. So some people say, well, it's easy to read, so we don't have to worry about it. Kids will get it. And that's just not true. And you'll see that throughout the day today. But are these print speech reorganization, this plasticity whereby areas of the brain that have evolved to talk and listen become available for reading and writing? Is this universal? Well, here's some data that I think you're going to have in your talk as well, Manolo, that we did together and published a few years ago in Proceedings of the National Academy. There is Manolo, and there's me and a bunch of people from China and Israel. And we looked at brains in 4 languages. And one of them was Spanish. And the color schemes are different, but you can now sort of guess. In green are the areas that are in the auditory cortex that respond to speech. In blue are the visual areas. And now in pink are those areas that are binding and changing and transforming. And what we found in that study when it comes to activation is it didn't make a bloody bit of difference whether it was a transparent language like Spanish or even a rather irregular one like Hebrew and Chinese. In general, this reorganization this transformation of perisylvian regions was identical across languages. There are subtle differences, but primarily the take-home was a good degree of universality. And why does this matter? To this audience, it matters to us a lot. And then we debate how exactly are they similar and what do we look at next, and lots of questions. But for this audience, I do want to share that what we see in skilled Spanish readers is the same transformation, the same reorganization that we are seeing in other writing systems, irrespective of their complexity or their depth. So there's at least a suggestion at the level of brain for universality. And so it's critical that we know this. Early experiences that promote language skills will help to build the triangle. And when the triangle is built in the brain, it sort of looks like this. Populations of neurons here, here, and there become a reading circuit. The reading circuit blends oral and written language, and if all goes well, you develop fast and efficient word recognition in the left visual word form area. What does this imply about reading? Well, this doesn't come from brain science, but brain science reinforces. Many of the speakers will talk about this today, so I'll just allude to it. We know that reading involves, pre-readers need language stimulation, vocabulary, appreciation of books. And we know that initial stages of learning to read must, mandatorily, no arguments allowed in this room, no, must involve an appreciation of phonologic principle. Okay, last piece, and I'll go quickly here. So the second question and the third is, how does all this look different in dyslexia? Is it different? Do we see differences in the way these circuits form? By the way, I'm going to say this again. Ready? The first question I answered the following way. How does the brain build circuits that allow skilled reading, fluent decoding? We reorganize major regions in the left hemisphere. We transform them so that print and speech bind. We create fast mapping systems in left cortex. That's what we know so far. There's a lot more we don't know, but we know this. And it appears to be largely universal. Agree? See. You do agree, don't you? We've not seen any difference in Spanish, my amigo. Anyway, okay, we'll let Manolo come later. So, now to the question of what does dyslexia look like in the brain? What does reading disability, struggling reading, look like? Well, what we find, first of all, is at a cognitive level, for the vast majority of kids who struggle with reading, and we have the experts here today, this binding, this grapheme-phoneme learning is extremely problematic and is usually rooted in earlier problems in oral language, including phonologic awareness. And we have new data that we've just published, and I can't bring it in today or they'll kill me, but showing that even in 4-year-olds, not just phonologic awareness, but the quality of receptive and expressive speech, modified auditory feedback, which is a very low-level speech task, is predicting reading. So early speech skills, I'll send that to you, Florencia, but early speech skills are predicting reading and are making it difficult to build the triangle. And so what does it look like? Question number 2 in the brain. I'm going to go fast now. What it looks like is that these left areas, particularly this important fast mapping occipitotemporal region, fail to behave coherently. They look noisy, the connectivity, the connections seem weak. We even see differences in gray and white matter volume. This is a study that was done in 3 languages, French, Italian, and English, and looked for a universal signature of dyslexia. This is by Araldo Palazu, and found that that area I was talking about that transforms itself to allow rapid, fluent mapping from vision into language, this visual word form, was disrupted or poorly organized, poorly activated in all languages in dyslexia. So, question number 2, how does the dyslexic brain look different? We see 2 things. We see a failure to develop coherent connections and activation in these important left posterior regions. And in that condition, dyslexic children often build altered circuits, including the non-dominant hemisphere, the right hemisphere, and the frontal lobe. Now, guys, listen carefully. We're coming close to the end. I've just said this is how typically developing readers read. They go here. And I've said that dyslexic readers, in the absence of treatment, effective treatment, tend to go elsewhere. Have I now explained the cause of dyslexia by having brain maps? No. I'm glad so many of you shook your head no. I've described dyslexia at the level of circuit. Why the dyslexic child's brain has a problem with these and moves elsewhere in the absence of treatment is a deeper neuroscience question. I won't be going into it today, but all of our labs together work at genetics and neurochemistry and lots of things that are meant to try to understand from the earliest ages why some bright, beautiful kids fail to develop these normal connections here and reading becomes difficult. But why is it important that we know that typically developing readers go here and atypically developing readers don't? Why is that important? And I'll tell you why. Listen. Because that provides a target for treatment. If we are on the right track for that child and they're young and the treatment is effective, then we know that we should be strengthening certain circuits, if possible. We don't know. Does treatment normalize these circuits, or does it simply strengthen the altered circuits? So by knowing how dyslexic look different, questions 1 and 2, how do typical and atypical brains build circuits, how do they differ? We have a critical information. We're not explaining yet. We should be humble. We shouldn't be bragging. But we do now have a target for treatment. And I just want to end by showing you that we've been using imaging lots these days in my lab and many others, to actually study at a very sensitive level of analysis how treatment works, why it works for some children, why it doesn't work for others, and how we might use that knowledge to improve the efficacy of treatment for larger numbers of kids. So we're basically asking these questions. Does good intervention normalize those brain differences that I've just spent my talk talking about? We were among the first to publish a large-scale pre, post, and one-year follow-up imaging study. We worked with a fantastic education researcher named Benita Blackman at Syracuse University. The imaging people like me are not the stars of this paper. All I did was map brains. It's Benita Blackman's education program, which is very similar to programs that Phyllis will talk about today, and I think we'll all mention, phonics and vocabulary and fluency. We were simply looking at the brain pre and post and asking the question, how much plasticity do we see in children with severe dyslexia? If the treatment is working, do we see a normalization of those pathways? And so the treatment we can go into this in the discussion later today. We got very good results, or else we wouldn't have done this large and expensive imaging study. And again, the left hemisphere is on the right, and those are the 3 components I showed you. And what we found is, from pre to post to 1-year follow-up, the treatment group, the children who were getting 90 hours, 5 days a week, were normalizing these connections, including this fast mapping system, and they were reducing, in purple, you can see they're reducing reliance on the non-dominant hemisphere. So this is a value, folks, of neuroscience, a little value, where we're able to kind of explore how learning works and how it changes the brain. But even here, you know, we have lots of evidence in lots of languages for some normalization, for some compensation. Pero, there's lots of questions we haven't answered, such as, why do the majority of kids with dyslexia who have very similar behavioral problems respond to a phonics treatment and some don't? And this is the promise. Listen, this is about the last thing I'm going to say. This is the promise of neuroscience, because we have this exquisite sensitivity to the individual brain. And what we're arguing is we can use imaging to understand not just how treatment works in responders, but also why it doesn't work in resistors. And by knowing where their fragile points are in brain, we can tailor treatments to those fragile points. And so the promise of neuroscience is to improve and individualize and modify instruction to the brain. We're not there yet, and anyone who says they've got a program that does that should be kicked. but we're getting closer, and this is where I want to end. So this is a study that we're currently doing with a large treatment study developed by Maureen Lovett called Empower. We're collecting data in Atlanta, and we're working with people in Toronto and at Haskins Labs, my lab, and Yale, my university. We are doing hundreds and hundreds of children, and we're imaging the brain during treatment, before and after. And we're asking this question: can we use neuroscience and neuroimaging not just to understand what treatment does when it works? We already kind of know that. But what are the brain factors that discriminate children who find it easy, even though they struggle, and respond to a conventional treatment versus those who don't? And so we're looking at very complex populations with reading disability plus ADHD or SLI, everything, a very complex population. This is the general treatment effect, and you can see that we are increasing activity. If I could show you the bottom of the brain, you'd see it as well. So the treatment on average is normalizing for many kids the left. But here is the critical thing. There are some kids who are responding well to treatment, and some who are responding poorly. And we are able now to see, even before scanning, what it is, which brain areas are most predictive of response to treatment. Now that we're doing this study, we will go to the next level, which is to figure out how we can work to those systems that are weak. So, to conclude, we know that reading is parasitic on early language. We've got some knowledge in answering those three questions. How does typically developing circuits build? What are the critical areas? What are the connections? We're even doing work that I'm not talking about because it would be torturing you to show you this research, the connecting genetics and neurochemistry and lots of imaging. That's what I'm currently working on. That's why my hair is gray. This project with my colleague Fumiko Heft. We are digging deeply into the mechanism. It's beyond today's, but if you're interested, or you're a student of neuroscience, I can send you more information. But where we are right now is we do have some understanding of the way in which the brain builds circuits, and how certain regions are critical and tend to be disrupted in dyslexia. And we have some preliminary work in multiple languages suggesting that good treatment can have a normalizing effect for many, but not all children. And now we're at a point where we're using imaging to go even more deeply into the richness of individuals, why some children are different than others. You all know as teachers the following: no two kids with or without learning problems are identical. Every human is unique and rich. The promise of neuroscience in the classroom, in my opinion, is the ability to use an exquisite understanding of the biology of learning that modern neuroscience provides to begin to tailor the treatment to the brain. Thank you very much for your attention.